Well, I'm going to take advantage of the time and say that the Southern Ocean, in case you don't know, is the ocean surrounding Antarctica that extends to about 40 degrees south. And what I'm going to be doing today is showing you reconstructions of biogeochemical change in the Southern Ocean over several glacial cycles, 1 or 2 glacial cycles, quoting CO2 declines that those biogeochemical changes during ice ages would be expected to cause, and from this basis proposing that the Southern Ocean is responsible for the major features of glacial and interglacial carbon dioxide change. Oh, sorry. So the work I'm showing has been done by this incredible group of people over here, and I have to acknowledge Gerald Haug, my long-term collaborator in this work, who is usually just a terrific help, but last night woke me up at 2 a.m. and can't seem to keep my eyes open, so he's got one demerit for today. So the modern Southern Ocean, many of you know, is a major leak in the global biological, the global ocean's biological pump. In the ocean, we have excess CO2 and nutrients stored in the deep ocean, but they are brought into the surface in the Southern Ocean by this strong overturning circulation. And because of limitations on phytoplankton growth in this environment, especially limitation by iron, phytoplankton are unable to completely reconsume the nutrients and excess CO2 that are brought to the surface. As a result, some of those excess nutrients, a lot of them, return back into the interior unused. I'm describing the nutrients here simply in terms of nitrate, and CO2 is evaded to the atmosphere. So this is the leak. So since the discovery of glacial and glacial CO2 change, of lower CO2 levels during ice ages, it's been recognized that if we could stem this leak during ice ages, we'd have a potential explanation for the lower ice age atmospheric CO2. And in this context, there are 2 scenarios, end-member scenarios, that one can imagine. One is simply that Southern Ocean biology, organic matter production on the surface and export to the interior, increased and thus consumed a greater fraction of the nutrients and CO2 that are brought up, stemming this CO2 release to the atmosphere. The end-member alternative, which I'll be describing as stratification through the talk, although that's not a terrific term, involves a reduction in the overturning rate through the Southern Ocean. This reduces the CO2 leakage by 2 ways. First of all, it decreases this overturning relative to other deep water formation processes in the global ocean, which in effect lowers this CO2 leakage. And in addition, even if phytoplankton growth is constant or even decreases during the last ice age and during ice ages, this production would have been able to consume a larger fraction of the nutrients and CO2 brought up from below. So again, stemming this CO2 leak. Now, the first type of work that people did to try to understand what the Southern Ocean did biogeochemically during the last ice age involved reconstructing export production by the flux of organic matter to the seabed. And in this work, what they observed was an increase in productivity in the Ice Age Subantarctic, but a decrease in the Ice Age Antarctic. So for the Subantarctic, there was some great excitement in the sense that it would be quite easy to imagine that this scenario would apply to the Subantarctic productivity increase. It was also recognized that there was an increased dust flux to the ocean during ice ages, which was what drove John Martin to propose the iron fertilization hypothesis to explain lower CO2. And so this has been something that people have been thinking about for a long time. The Antarctic was at first, I think, sort of depressing this observation of lower export production in terms of the entire Southern Ocean playing a major role in glacial and interglacial CO2 change. Here, export production was observed to decrease during glacials. So if the Antarctic, if you were going to be optimistic and argue that the entire Southern Ocean was working to reduce CO2 during ice ages, including the Antarctic would have to be operating by this type of scenario, the stratification scenario. Now, one prediction that both of these scenarios would make is that the degree of nitrate consumption would become more complete in surface waters the nitrate concentration would fall in surface waters, and we should be able to detect this as an increase in the N15 to N14 ratio of the organic matter that's produced in surface waters and exported to depth, an increase in the N15 to N14 ratio, and this is the same as an increase in the delta N15. The first work that was done on this used bulk sedimentary nitrogen, but bulk sedimentary nitrogen is vulnerable to diagenesis and to contamination, and so today I'm going to be showing you data from organic matter bound within microfossils and diatoms in the Antarctic and foraminifera in the subantarctic. So now we're going to look at some data from the Antarctic. This is a core from the Pacific Antarctic sector. The data from the core is down below. There are a couple of curves from the ice cores up on top. So here we have atmospheric CO2 from the ice cores and reconstruction of air temperature based on deuterium from the ice cores as well. And these, on this time scale, we've got the ice ages here, the interglacials here. So the blue is the deeper part of the ice ages. The data from the is it counting down? Good. The data from the sediment core is shown down below. So on the bottom here, we have two proxies for the reconstruction of export production. And just as I said, they indicate that there's lower export production in the last ice age and in previous ice ages relative to the interglacials, as has been observed before. Now, above that are the diatom-bound nitrogen isotope data, and there are two records here. Both of which make me thirsty. There are two records here. The distinction is not particularly important for today, but they are actually independent records, and so they give you some sense of our ability of our measurements to reconstruct the relevant patterns. What these records show is higher, so I should say N15, N14, or delta N15 is plotted increasing downward here. So increased nutrient consumption would be downward on this plot. Higher surface nitrate concentrations would be upward. So what we're seeing for the ice ages is more complete nitrate consumption, lower surface nitrate concentrations during the ice ages, and yet this is when, these are times when export production, biological productivity, appears to be lower. So the only way for both of these things to be true, higher degree of nitrate consumption, but lower export production, is that there was a reduction of nitrate supply from below, i.e. something like that stratification scenario I proposed to you, I showed to you earlier on. Now, how much CO2 decline would one expect from this change? If this change applied, we could think of this as being a applying generally to the Antarctic zone. Box model simulations would suggest that the CO2 drawdown one would get would be something like 35 to 50 ppm. Lower numbers tending to apply when you're imagining this occurring in the context of North Atlantic deep water circulation such as we have today. Higher values tending to apply if you imagine glacial North Atlantic intermediate water forming in the ice ages. One other interesting thing I want to point out here is that the diatom-bound delta N15 rises begin quite early in the glacial progression for the last glacial cycle. With the end of the previous interglacial here, we start to see the first increase in diatom-bound delta N15. And so this 35 to 50 ppm CO2 decline can be applied to this record starting from that time forward and may help to explain, for example, the CO2 decline we see over this period, as well as some of the CO2 decline that occurs later on. Okay, so now let's move on to the subantarctic. This is a core from the subantarctic Atlantic, the work chiefly of Alfredo Martinez Garcia. So the data here we have on the x-axis age again back to 160,000 years ago. Again, we have some data from the ice cores plotted as well. So this is the CO2 record up there. And down here, we have Antarctic dust accumulation. It was these types of data, a lower resolution form of this, that drove John Martin to propose the iron fertilization hypothesis. Higher dust fluxes to the Southern Ocean during the last ice age. The idea would be, would fertilize the Southern Ocean with iron and increase productivity. Quite remarkably, at this sediment core, the iron fluxes follow the dust record seen in Antarctica quite well. So that's shown in the black curve up here that's covered by the red stuff that I'll get to in a second. And so these dust fluxes that applied in Antarctica also change, these dust flux changes that applied in Antarctica also applied in the subantarctic, and at this site in particular. Now, one thing that's been known for some time, and it is shown quite nicely here, is that productivity was higher during the glacials in the subantarctic. And you can see that it's even a finer thing than that. This is a reconstruction of export production based on alkanone accumulation rates. At each time when dust fluxes are high, at the millennial scale as well as in general, we see higher export production. And so these types of data alone have made people very interested in the possibility of iron fertilization occurring in the subantarctic. However, if that's true, what we should see during each of these rises in export production is a decline in surface nitrate concentration, an increase in the degree of nitrate consumption. Now, shown in the red data up here are the delta N15 measurements. The red points up here are the delta N15 measurements on the foraminifera G. beloides. And here, delta N15 is plotted upward. So higher degree of nitrate consumption would be upward. Higher surface nitrate concentrations would be downward. And you can see that the correspondence is quite remarkable. Whenever there is high dust, there is high production, as we know, and there is also a higher degree of nitrate consumption. It's very hard to explain these data in any other way than iron fertilization. Now, the type of CO2 decline that we're talking about here that one would expect from these type of changes is also on the order of 40 ppm. Some of you might be surprised by that relatively high number, given that the subantarctic ventilates a relatively small volume of the ocean interior. Just hold on to that surprise for a second. The reason you do get such a significant CO2 drawdown is the subantarctic also affects the depth distribution of regenerated carbon in the ocean, and it also affects the rate of low latitude production, and thus calcium carbonate rain to the seabed across the global ocean, and these things feed back on alkalinity. So the subantarctic takes advantage to a substantial degree of changes in ocean alkalinity to drive part of this CO2 change. The next point I should make here is that within the last glacial progression, you can see that dust fluxes, and we've known this for a while, don't begin to rise until well into the glacial progression. And of course, export production and the first really large changes in delta N15 occur at that same time. So this is the type, this iron fertilization seems to be something one might apply to the latter part of the CO2 decline associated with ice ages. So not to be too pedantic about this, but the argument I'm making here is that Antarctic versus subantarctic changes are both contributing to glacial and interglacial CO2 and the CO2 drawdown over ice ages, but with a different pacing within the glacial progression. So shown on this axis here is, and these are model results, is PCO2 decline going downward here. The Antarctic experiments compiled up here in terms of CO2 decline are shown here. So about, in this case, shown as 38 ppm, 37 ppm. And this, given what I've shown you, one might start to apply right at the MIS 5ED transition, early in the glacial progression. And then these arrows here are for subantarctic zone iron fertilization, as well as the switch to glacial, from NADW to glacial North Atlantic intermediate water formation. And these, based on the data I've shown you, could be reasonably applied from the 5-4 transition onward. And these together, when you bring them together, can get you to a CO2 drawdown that's greater than 80 ppm, or quite close to the observations for how much CO2 is lowered during ice ages. Now, I want to end up by talking about how these things unwind in the deglaciation. We have less information about this right now, but I'm going to show you some of the things we have. We're going to talk about the deglaciation in Antarctica. So the data on the left here are what I've already shown you, but now just blowing up in the last 22,000 years. We have, again, these same ice core thingies up above. Down here, we've got the reconstruction of export production change. And here are the delta N15 data, again, plotted higher, plotted downward. So what we see is, at this time, an increase in export production a decrease in the nitrate consumption, and so it looks like the unwinding of the stratification that applied during the last ice age. Now, there's an early part to this, so something that one might imagine applying to part of this CO2 rise early in the deglaciation. At the same time, there's an awful lot of continued delta and 15 fall through the Holocene. Now, we were pretty uncertain about this. I could tell you about our tribulations with age models in these Antarctic sediment cores. But we also, beyond age models, we were worried about how regionally expansive this signal was. And so we now have some new data from the Indian Antarctic. And without belaboring this greatly, these here are the diatom-bound delta and 15 data. They really are there. These red and black over here, for the Indian Antarctic core. And here are some proxies, here are some proxies for export production, similar to the ones that are used over here. And again, we see an increase in production and a decrease in nitrate consumption, with the first part starting quite early in the deglaciation, at the beginning of what people refer to as HS1, but then much of the further decline in delta and 15 occurring through the Holocene, much as observed in the Pacific Antarctic. So we're starting to believe this Holocene trend. Now, this offers both possibilities and questions. And for the kind of possibility it raises is that this CO2 rise that has been mysterious, occurring through the course of the Holocene, might be explained by this continued Antarctic destratification over the course of the Holocene, something we didn't expect to see. At the same time, it means that you can't imagine that this destratification applied all to the HS1 interval. And so some of this CO2 rise is going to have other origins. And I don't have the time to defend this now, but the data that we have for the subantarctic would suggest that this change did unwind quite early in the deglaciation. And so we do believe that a lot of the loss of iron fertilization would have applied to the early CO2 decline. And there's also deep ocean warming that's occurring over this time period. And we've just heard something very relevant from Andreas on this matter as well. Okay, so to summarize, I have the atmospheric CO2 record for the last glacial cycle in the middle, flanked by the oxygen isotope record and Antarctic air temperature and so we have the interglacials here and here. And so what I'm proposing is that starting at the end of the previous interglacial, the 5ED transition, Antarctic stratification began to apply itself. That drove some of the early CO2 declines, and this continued through the full glacial, to the last glacial maximum. And then it unwound, starting in the beginning of the deglaciation, but also continuing through the Holocene. Subantarctic iron fertilization appears to have begun about halfway through the glacial progression and may explain this latter part of the CO2 decline. And it appears to have unwound quite early in the deglaciation. That's it. Thank you.
Quick question, and then we have the other group coming in. Anyone? Ed.
Danny, one of the ice core observations is that some of the CO2 changes during the deglaciation are very fast. So are there limits, do you think, on how fast the mechanisms you're talking about can happen?
Yeah, so a couple of comments. Let me say that Sean, in his email about this session, mentioned these rapid changes, and my talk ended up ignoring them. And that's because I thought I would run out of time, actually. So we do have something to say about these fast transitions in the deglacial, but it'll be maybe some other time. That said, the deep ocean overturning changes, they have a very fat. They have a long component, which is the calcium carbonate component, which is thousands of years and isn't relevant to your question. And they have a fast component, which involves the venting of respired CO2, and so does sea ice retraction. Both of these things are kind of comparable in their ability to release CO2 quickly. And when I say quickly, a lot of it is done in box models, in 200-300 years, I'd say 50% is done by then. And of that, you could back some of that up to literally occurring, the first blast, I think could occur in decades. I mean, I'm not saying that I know that those really rapid changes can be driven by ocean processes, but I think that they can.